Our next step is to calculate the modification factors that are relevant here. Let's go to the formula sheet. The equation for the final equation for the ascent curve that we have are these following. So I'm just going to copy these equations over there, Control C, and so we can start using them. So now we're going to look at the modification or the modifying or the modification factors. So now what we have in this case, as we have it from the formula sheet, we already calculated KF and KF accent, the fatigue notch factors. But we still need to look at modifications for size, load, surface finish, temperature, and reliability. Now, let's do them in the order as they are there. Let's first look at size. If we go back to the problem at the top, it says here in terms of size, what does it say there? It says the shaft has a radius of 300 millimeters. We can assume that this is a shaft that's operating here. They say the shaft is loaded in axial loading. It's maybe more a hypothetical problem because normally shafts are rotating, but yeah, it's axial, so we need to model that. And then they say the shaft has a radius of 100 millimeter, and that's basically all that they say. So let's go to the size modification factor. The shaft, the part is a shaft with diameter 100 millimeter. Now, in our formula sheet, I've given you equations that we use to do size modification factors. Here is one equation that we use for size. Let's see if it's applicable. Yes, 1 for less than 8 millimeter. This is a 100 millimeter shaft, so yes, we can use this one, Control C. Let's go back to our formula sheet. So this size modification factor is that one. Now in this case, the diameter is more than 8 millimeters, so we sit here with 1.89 times diameter. Now they say diameter in millimeter to the power minus 0.097. That's how it seems. And if I now get my MATLAB open here again, I can see my C size in this case is equal to 1.189 times 100 to the power minus 0.097. And there I have my size modification factor, 0.76. So that's my size modification factor. And that is done. Then we can look at the next one that they want is the load modification factor. Now, we've spoken in the class about load many times in terms of shear and in terms of bending, in terms of axial loading. And the most important one that we have in this case that we need is this one here. Remember, Dowling's handbook has got many of different examples there for size for load. And they also have very different ones for size. So make sure you take care of that. It's given in the table there. Now let's take this one. The loading. If a test was done in bending, it's a smaller volume that's subject to the cyclic stresses. Now we have a specimen that's subject to an axial loading. So we need to model for that axial loading, and for that we use the size modification factor. And the size modification factor is that one. Now let's go to our problem. Now let's say, in this problem, the specimen is subject to axial loading. The SN curve parameters were, the SN curve, let's say just the SN curve were estimated for using equation for rotating bending test. Therefore, a modification must be made for load in this case. Now, the equation that we have at the moment is this one here. If we have the endurance, the stress in the axial loading is equal to 0.7, the one for subject to bending. So in this case, we have, alt nu EI C load is equal to 0.70. I'm just going to put that in my MATLAB as well, so that we can simplify calculations. So here we have C load is equal to 0.7. Good. So that's a load modification factor. Let's look at the next one. The next one is surface finish. Now, in the notes, we've spoken about surface finish a lot and its effect on endurance limit. So I'm going to make here surface finish. We go to our notes, our formula sheet, or our notes. I've given you a curve that looks like this. Now, this curve gives us the surface reduction factors or the surface modification factors for surface finish. There are also equations that you can use for surface finish, but this is the one that we typically apply for surface finish. There are many other relationships for different materials that you can use for surface finish that takes into account the sensitivity to the higher ultimate tensile strength. In this case, we're going to use this one to model the surface finish effect. Let's go back to our problem. So the surface finish modification factor, in this case, I'm going to make this large, right? I'm going to go to the next page here with the surface finish factor. And for our surface finish factor, let's look at the problem. Now, we have a material with an ultimate tensile strength of 1050 MPa, or about 151 KSI, 154 KSI, around about there. So I'm going to insert a line from the 1050, so this is 1500, this is 1250, 1200, 1100, 1050 is approximately there. Then I go to my machined surface, to my machined surface here, and then I'm going to insert an additional line to the left to read off my factor, and if we put it in there, it seems as if the load factor for, now let's make this one that is 0, it mustn't go up and down. The load factor is the surface finish factor is approximately 0.67. What did I do now? Control Z. Good. So for this, I can say C surface finish is equal to 0.7. Right, that's what we have. So there we have the surface modification factor. I'm just going to put it in my MATLAB so that when I want to do calculation with it, I have it 0.7 here as well. Right, this surface is 0.7. Let's go back to our formula and see what we need. Now we need temperature, a modification factor for temperature. Now, there are several equations that we can use to modify for temperature. If I go to the formula sheet, the one that I've given you on the formula sheet is this one here. It covers the temperature that we have in this case, which is 200 degrees Celsius. It goes up to 550 degrees Celsius. You can also use this modification reduction factor for temperature, where you take this curve, which comes from the International Institute of Welding. That's a modification factor for steel. And they base it on the sensitivity of the modulus of elasticity to temperature. So if you can calculate, according to them, the modulus of elasticity of at an elevated temperature versus that one at 20 degrees Celsius, that will give you your reduction factor for temperature. Now, in this case, we use this formula here. So let's go back to our problem. So from the equation below, alt nu EI, CT is equal to 1.0. How do I know? Because it's 1 for less than 450 degrees Celsius. And in this case, we have a temperature of, if I remember correctly, 200 degrees Celsius. That's how I remember it. The temperature was 200 degrees Celsius. I can go to the problem quickly. Yes, temperature was 200 degrees Celsius. Now, the next one that we need to look at is our reliability. Now, reliability has got to do with probability of survival. Now, let's put the new one in here so that we can work with reliability here. Our reliability modification factor is again coming. Let's go to our formula sheet. I've summarized them in your formula sheet. Let's take this one here and take it to our problem. Now, if we look at the probability of survival that they want in this case they want this is 1 minus probability of failure that you see here. Let's make it bigger. What you see on this table here, it's just a normal distribution. So here they have 1 minus probability of failure, which is probability of survival. They wanted a probability of failure of 1%. That's 0.01. That means they want a probability of survival of 99%, which is 0.99. Now let's block it so that we can see where we are. So we're going to look at this one here. That's our probability of failure and survival that we're going to work with. So I don't know what happened here now. It doesn't want to. Okay, there's the enter now. So let's move this one up. So we can say from the table below, alt nu EIC for reliability is equal to 0.814. I'm just going to put that in my MATLAB problem, and in the next video we will continue with calculating doing the mean stress correction and calculating the damage. There we are.